Good evening, everyone. Welcome to week 10 live interactive session of good evening. Week 10 live interactive session of ACN. Exactly. So in the am I audible? Can you just confirm once? Okay, thanks. Then we'll get started. In the previous, okay, let me share the other screen and then we'll get started. So in this week, the major topics it's a continuation of the data center networking and the new protocols that emerged as a requirement for data centers was discussed. So the first protocol that was discussed is DC-TCP. Then there was a discussion on in-band network telemetry, INT, and then serverless computing. We'll briefly take a look at what these concepts are, and then we'll go to the MCQ questions from the previous year. Well, I'll keep the session little short as I'm not keeping well. So yeah, well, let's get started. Let's start with the DC-TCP. Yeah. So I think we all know about TCP. TCP is a transport layer protocol which like in the TCP IP hierarchy, we have the physical layer, the link layer, the IP layer, and the transport layer. This is the application, and this is the transport layer. So in the transport layer, we have TCP protocol and UDP. So TCP is basically connection oriented, and it takes care of the delivery of packets. It takes care of the delivery, and also it is reliable due to the acknowledgement mechanism. In addition to that, TCP also have this congestion control mechanism. So when TCP starts up, when a TCP connection is established between two parties, we have the SYN ACK and SYN-ACK exchanged. SYN, SYN-ACK and ACK exchanged, and that's how the first connection is established. And after that, the packets, TCP starts to send the packets based on the window size. So this window size is something like how many bytes can be in transit at a given point of time. So slowly TCP will increase the window size. So we have this slow start mode. Slowly we will increase it, and at some point we will see that okay, the congestion happens, and then the TCP size will be reduced by 2. Again it will go. So this is the typical, this is a this is a typical TCP window, sliding window mechanism. This is how the window grows. Then again, TCP actually grows until and causes congestion, make sure a packet gets dropped, and then it do a congestion control. That's how the normal traditional TCP mechanism works. So in data center, with the data center network, this particular TCP protocol, which is actually optimized for wide area network. The doesn't actually serve well for the DCN, because there data, the patterns of are slightly different. How the applications communicate is slightly different, and the RTT, or the latency expected, is also different. So in the previous class, we have seen that in data center networks, we have something called as we have a lot of racks wherein the servers will be there, and we will have in the there will be a topology from outside packet will come, it will come here, and then sometimes there will be a lot of east west traffic that communicate with the various applications, and then the request, external request, will be processed, and then the response will be sent back. So this is how typically this is how the data center traffic is, which is very different from, however, normal WAN traffic. So DCN traffic is very different from WAN traffic, and also the latency is very low here in terms of microseconds. Between east-west traffic, the RTTs are very low. So with these issues, with these the this TCP, with TCP in the data center network for the specific application workloads that we normally run in the data center, we were having people were facing issues in the data center network, and one of the major issue that led to the invention or the proposal of TCP is the TCP incast issue. So let's see what this TCP incast issue is. So, as we have seen in the previous class, typically in the data center, topology will be like, we will have the internet, we will have the core routers connected to it, then we will have different aggregation layer of switches running here, and then there will be another, I mean, depending on the topology, fat tree or leaf spine, it will vary, and then we have the racks. So this is our typical DCN, and this is symbolic representation. So we will have this connected. May not be exactly correct. Okay, so there are connections across drawing it. This is our typical DC topology looks like, and when a request comes from the external world, a typical let's take an example of a web search query such as Google search. Okay, so when a request comes from this, it will go all the way, and probably it will reach this particular server, and these search queries are typically handled as using aggregators and worker nodes. So the query will first reach what is known as an aggregator, and the aggregator will split this query among multiple workers: worker 1, worker 2, worker 3, worker 4, worker 5. Then these workers work on the query, and they send it back. The response will be sent back. Then the aggregator will aggregate the responses and send it back to the original user. So this is how typical web search or Google search kind of queries work in the data center. We call such workload patterns as partition aggregate patterns. Okay. These kind of workloads are normally called as partition aggregate patterns. So the aggregator first partition the query to multiple pieces. Then one on receiving the response, that is aggregated. The response is aggregated and sent back to the user. Okay. So what happens is typically what happens is We have seen, right? Every rack will have on top, there will be a top of the rack switch. So we have this switch here, and this port of the switch is connected to the aggregator or the parent. You can call him the parent. Now this aggregator, on receiving the request, will send it to worker 1, W1, W2, W3, W4, W5. Okay, so from the parent, the request will be split, and it will be given to worker 1, worker 2, worker 3, and worker 4. Now all of them will work and then respond back. W1 will respond, W2 will respond, 3 will respond, 4 will respond, 5 will respond. And majority of the times, since all of them kind of responds at the same time, all this response go to the same outgoing port in the switch. Right, it has to go to the parent, which is suppose connected to port 1 of the switch. So all the responses from all the aggregators, or sorry, all the workers go to this particular port. So what happens is, since there is this is the reason why we call it as incast. There is an incast or an inflow of lot of responses over to this parent. So this egress, we call this egress, the packet have to egress out of this interface, right? So the egress port buffer gets filled because a lot of packets comes together to the egress port. Its buffer gets filled, and because of this, packet drop happens. Now when packet drop happens, the aggregator will have to wait for that, right? For example, if the worker 3's packet was dropped, so aggregator or the parent will have to wait for that packet to be received, so that the aggregation can be done and then the response can be sent across. Okay, so this is one major issue with TCP that was observed in the data center workloads. Okay, so now what happens is, when a packet drop happen, we know how TCP responds, right? TCP will wait for retransmission timeout, right? There is something called retransmission timeout until that timer expires. I hope everybody have this basics of TCP. So whenever, I'll just quickly go through, when a data sends, so it actually starts a retransmission timeout for every packet corresponding to each packet is identified by a sequence number. So every packet, it starts a retransmission timeout, and when an ACK is received, acknowledgement is received for that particular packet, the RTO will be stopped. So if I send a packet, and if this packets gets dropped, the I have this retransmission timer. For example, by default it is 300 millisecond. So this 300 millisecond timer will be started, and then until the timer expiry, if I don't get any acknowledgement corresponding to this packet, there is no app corresponding. So RTO timer expire, then TCP will do a retransmission of the same packet. So this is P1, this is ACK of P1, P1 ACK. This is P2, P2 got dropped, no ACK was received, so P2 will be resent. So until the retransmission timer expires, TCP will not be sending the retransmitting the packet. So at the aggregator, this actually delays, so which can also lead to the request response getting delayed for the particular request. Mm, So for more for example, we have worker 1, worker 2, worker 3, and worker 4. And on the switch, suppose this is the queue that the switch has. And this is the egress. I have told you, no, egress port 1. So let it this be the buffer that the egress port P1 has. So with all the packets coming to this, so packets get accumulated and it gets filled up and then it starts to drop. As the packet gets a buffer is full, packets gets dropped. Okay, so if whichever workers packet have been dropped accordingly, that particular packet will be retransmitted after the RTU timeout, and then the aggregator will be able to continue with the processing. So, so the major problem is this time here, because it has to wait. So if we see that I have started this packet maybe 1 second, I got it at 1.2 and I send this at 1.3. Now I'll be this after 1.3, 300 millisecond has to expire, right? It's in millisecond, so it will be 301.3 millisecond. That is when I'm sending the packet. So this is a huge number when compared to the TCP's like sorry data center networks RTT. In the data center, the RTTs are in the range of microseconds. So having this large delay is will impact. So one obvious choice would be why can't we reduce the RTO accordingly? But the problem is that if we reduce the RTO accordingly, sometimes if we reduce it too low, if we keep the RTO as too low, so it can so happen that if we keep the RTO as probably maybe 50 microsecond or 100 microsecond, then it can happen that this particular packet, okay, this I got the ACK, P1 ACK, but P2 I have sent it, and P2, this again RTO have started and RTO expired here, but I am getting an ACK after maybe 150 microsecond or so. So what happens was P2 was actually buffered here. P2 was buffered in the queue, and so it took some time for P2 to reach the aggregator and the ACK back. So if we keep RTO very low, then what happens is a lot of retransmissions will increase, and thus again it will lead to buffer overflow. Retransmissions actually increases the number of packets in transit, so that actually can have a negative impact. So reducing RTO to mitigate this is not a good choice of solution. Hmm. Hmm. In addition to that, another issue, data center networks normally observes or another traffic or another characteristic of the traffic that data center networks observe is that the traffic or the flows can be majorly classified into short-lived flows short-lived flows or long flows. Sorry. Also called as mice flows, also called as elephant flows. Okay. So, in general, short-lived flows are latency sensitive, and elephant flows are demanding high throughput applications. Okay. So, another issue that normally happens is that in general, uh, so, Yeah, another issue is that sometimes the in general, each port have its own buffer in the switches. Each port will have its own buffer, but in some low end switches it so happened that the buffer across gets shared. So in such cases the resources gets shared between these shared between mice flow and elephant flow, and these elephant flows eat up all the buffer, and mice flows end up suffering. This is another issue that data center networks were observing. So the industry folks who have the disease up and running, Google, Facebook, and all, came up with their own workarounds to fix it. So Google came up with a solution wherein it was compressing the responses such that they could reduce the number of TCP packets. Facebook also had a similar kind of a different kind of a workaround. So with this issue in place, the community came up, and TCP was designed. So the goal for DC-TCP is to achieve low latency and no queue buildup. And it has to also work with shallow buffered switches. And we do not have to modify the applications, the switches or the routers. So major idea was to use something called we have something called explicit congestion notification, which actually is a mechanism wherein the switches will check the buffer queue length. Queue length is checked, and if queue length greater than some threshold, which it may like around 70%, if the queue length is already 70% or 80% of its capacity, it means that the queue is gonna get filled up, and thus a packet drop can happen. So when the queue length is greater than the threshold, it's a potential congestion scenario. A bit is set called explicit congestion notification. A bit is set. Mm. And this will indicate the sender that okay, there is a potential congestion that is going to happen, so let me slow down. So this is how ECN works. So here we don't wait for, so with ECN packet loss doesn't happen. Packet loss does not happen because because ECN sender slows down before queue becoming full or packet getting dropped. Okay. So, but the issue with ECN is that irrespective, ECN was not looking at the number of packets that was having this mechanism. Like irrespective of whether how the source was responding was irrespective of one packet having ECN bit set or n packets having ECN bit set, the sender used to respond the same way. So it was like a binary mechanism. Either congestion is there or no congestion is there at all. So there is no proportion of congestion. For example, irrespective For example, if we had some 10 packets sent, P1, P2, P3, P4, P5, or maybe P6, and of this only P3 had this ECN bit set. Of all the others had it 0. So, but here also the sender will respond by making reducing the window size by 2. Window size is reduced by 2. Now, assume that all these packets had congestion bit set. Here also the window size is reduced by 2. So it doesn't look at um, mm, the proportion or the gravity of the congestions. For example, if the queue is slightly uh, okay, we have packets like this and our queue is still here. So probably it just reached here and maybe that's the reason only one packet got the congestion bit set. This could be the scenario in the but second one could be like this, right? So here actually it has to respond more aggressively. So this doesn't happen with ECN. So in DCP, they kind of try to turn the single bit scheme into a multi-bit scheme. So that is the idea here. Are you able to see my screen?
No.
Oh,
Yeah, no, no. Yes.
I mean, for the past couple of minutes, you were not able to see, or just
No,
few
now it's
seconds
visible. No, we were able to see.
you were able to see, right? Recording. Okay, give me a minute. Yeah. So in DC-TCP, the idea is to convert the single bit stream into a multi-bit stream. For example, if we have like so here instead of reducing the window size by 2, we have cut the window size based on the fraction of marked packets. So that is the basic idea. So instead of looking at the bit and taking a binary decision, we look at the bits for a period of time and then count how many packets during that period had the bit set, and then take a decision in proportional to the number of mark packets. So for example, if we have some 10 packets, if you observe, like for 10 packets, 10, of the 10 packets, now 8 packets have observed a ECN, have the ECN beta set. So normal TCP, it will do the window size by 2. It will do window size by 2. It will reduce it by, whereas with DC TCP, what they are trying to do is, of the 8 8 out of 10 packets have observed ECN set into 1 by 2. Normally, we reduce the window size by 2, so a fraction of it. So it is 4 by 10. So instead here we are making it 50%, but with DC TCP we are making it a 0.4, that is 40%. Now in this example, in second example, here 1 out of 10, right? 1 out of 10 have observed, which is 0.5, right? 0.05. So, which make it to 5%. Give me a minute, I'll be right back. Sorry, I'm not feeling well. Yeah. So with DC TCP, we will be reducing it by 5. So if you see the window size variation in typical TCP, we see this typical sawtooth pattern. We just keep varying uh, like this. Whereas with DC TCP, this actually keeps the variation is much lower. So that is the what we try. So the major advantage, or what DCTCP will try to achieve by this is, like, it tries to keep the queue length within a particular limit. So it ensures that there will be enough headroom for the packets that comes up. So it will maintain the queue length at a particular threshold, such that during the microburst or in cache time, when packets comes in, there will be buffer headroom will be available. So this is the idea with which DCTCP works. DCTCP mitigates incast by creating large buffer headroom. So if you see here also in normal TCP, when there is a there is a buffer becomes full, so a packet drop happens, and then the congestion TCP goes into the congestion control mechanism. So it actually reduces the window by half, and after that, what happens is after the congestion control phase, the buffer size actually goes down. Then again, the buffer will shoot up with the slow start. I mean, then again, when it reaches the congestion, again it goes down. So this is how typically the queue length or the buffer size typically varies for a normal TCP. But whereas for hmm, DC-TCP, we don't wait first of all for the congestion for the buffer to be full, and once it reaches the particular threshold, the based on the number of packets that get set, either based on the current number of packets that gets the ECN bit set, it actually varies minimally within a minimal range. It doesn't go off like from here. It doesn't go all the way like it. For example, here if this is the threshold, it doesn't go like this. It doesn't go that way. So that is the advantage of having DC-TCP. So we try to maintain in normal TCP. If you see that the buffer size will come down like this, like this, like this, whereas in normal TCP, it always tries to maintain the buffer size. It never reaches the full size. It always try to maintain the bus. I mean, slight variation will be there up and down. And if this is the full size, this much free buffer space is always maintained to incorporate the microburst. So that is how DCTCP actually handles the incast problem. Now let's take a look at the questions from the DCTCP section. Then we'll go to the second section. Yeah, so the one question is, um, which of the following statement is bar are correct? DCTCP. It provides high burst tolerance and low latency. B. DCTCP can help alleviate losses due to buffer pressure. drops packets indiscriminately to reduce network load. MD, this is ECU. Congestion to the sender. Before packets are dropped. Yeah, so what is the answer for this question? DC-TCP, which of the following statements is correct? Can you check and type in the answer? Yeah, so that is correct. A is correct. It uses ECN signal, ECN to signal the congestion to the sender before packets are dropped. This is correct. In addition to that, DC-TCP provides high burst tolerance and low latency for short flows. So this is one need. The burst tolerance is what is needed for solving the incast issue. So that is also true. So DC-TCP is tolerant towards burst because it always maintain a high buffer headroom so that even if a burst of packet comes, that can be accommodated. So because of that, it also ensures low latency for short flows because of the buffer headroom. Help alleviate loss due to buffer pressure. That is also true because it always maintains a minimal buffer with uh, room for burst traffic. It actually signals before the buffer getting filled only. It uses ECN signals to inform the sender, and also it maintains the buffer headroom. So it help alleviate the packet losses due to buffer pressure. So this is also true. Drops packets indiscriminately to reduce network. No, it doesn't happen. DC-TCP doesn't drop the packets like that. It actually it's a proactive mechanism rather than a reactive mechanism. So the statement about DC-TCP is wrong. It doesn't drop the packets indiscriminately to reduce the network load. That is wrong. Whereas the other three statements are correct. The other question that we have from DC-TCP is we have only one question from DC-TCP. Now let's move to the other part. So based on previous year's questions, I'm just discussing the topics and then looking at the questions. So this year also you would have got similar kind of questions. Now let's move to INT. INT, yeah. So INT is in-band network telemetry. So the data center networks, as we have seen, have actually led to the invention or the proposals of new protocols and mechanisms. Because in the traditional network, we had I mean, the WAN and the WAN architecture. The characteristic of the traffic flowing there and the characteristic of the network is very different from what we have in DC. So for DC, it's first of all, it's in a single administrative domain. The kind of traffic and the application that is run there is different. And then, like the kind because in DC, it's like Amazon or Microsoft or Google. They are actually providing the services, right? Like cloud services to the public, to various people. So people use this cloud in different ways. Like we will get to them. There are various ways these providers provide the cloud service. One could be as infrastructure, the other could be platform, it could be software or that. So the 10 we call them when I'm consuming a cloud service, normally I'll be called as a tenant. So when tenants are paying and using their service, right, the expectation is that the DC network and the infrastructure should be up and running all the time. So for example, I am hosting an application of mine in the Microsoft Azure or Google Cloud or wherever. My expectation is that anybody who's trying to access my application should be able to access it 24 cross 7 without any issue. There should not be any outage, there should not be any issue, any of my users should be facing it. So when these providers, cloud providers provides these services, it's very critical and important for them to ensure that they maintain the infrastructure properly. And even if something goes wrong, they should be quickly able to figure it out what went wrong, where, and they should be able to fix it. For example, if some by any chance if particular switch went down or a link went down or something wrong is happening in a particular switch, they should be able to have the observability and the monitoring capability. We should be able to understand that okay, something is wrong in the switch, we need to go and figure it out. So that should happen very, very quickly. So basically monitoring mechanisms should be in place. Monitoring, so DC requires, or the cloud providers needs an in-depth monitoring mechanism to make sure that their infrastructure is up and running, and also in case if there is any issue, they should be able to identify and fix the issue. So that is the idea here. So we have already seen how the data center network looks right? So we will have the cloud here, we will have the core router which gets connected to the aggregate switches. Then another layer will be there based on whichever topology, well, if it is a leaf spine or if it is a factory, accordingly the topology, I mean, it's a rough figure, okay. So, and it's a very small figure. This is not the scale at which these people operate. They have hundreds of switches. I have just drawn 1, 2, 3, that's all. So we will have the racks here, okay. Now, if from this rack, if I'm sending a packet, it has to go here, come here, and then come here. So, if by any chance, if this particular packet, and the response will come in the reverse direction. By any chance, if this particular request response is delayed, Hemalata, could you please mute yourself? So when a request goes from this particular application running in the server, and a response come, if by any chance if there is a delay observed, they should be able to know that okay, what went wrong where, and they should be able to figure out which path, with respect to there are multiple components here with respect to observability and monitoring. There are multiple components involved. One is this each server. Within the server, there could be issue, or the issue could be in the networking side. So one should be able to figure that out. Now let's take the networking part alone. That is this particular area. One should be able to know like which path the particular when a request is going, which switches it is traversing, which path it is traversing, and on the path, what is the queue size it have encountered. I mean, different people will be interested in different kinds of metrics and parameters to look at the network. Okay, so with the advent of programmable networks, we have already seen, right, in the last classes, what is programmable switch, programmable network, and all that. So with the advent of P4 and programmable switches, uh, one could actually, if this is a programmable switch, if this is a programmable switch, this is a programmable switch. If these are programmable switch which can be programmed using P4, I can actually program the switches in addition to its normal functionality. I can also program the switch to collect these network statistics and provide me for the monitoring purpose. So with this use case in mind, this in-band network telemetry, it's a specification. This came into picture, which tells us what lays down a specification that can be followed. Using which the network monitoring can be done, like which we can tell which flow I want to monitor, and which aspect of the flow I need to monitor. Like, do I want to monitor the congestion aspect or the queue length, or do I want to just see the drop packets? Those list we can actually provide. We can configure accordingly. So, in-band network telemetry gives a mechanism or a specification that helps us monitor the data center network. We will see in detail of how it is done. So in the traditional earlier days also, of course, monitoring mechanisms were there. There is this net flow and other things from Cisco and all, but it doesn't give a fine-grained visibility. So earlier mechanisms were all sampling based approaches, and only if the switch supports this monitoring, it can be done. For example, Cisco had its way of it had a support. So if the switch have it, then that can be utilized. That monitoring mechanism can be utilized. But I cannot have a tailor-made mechanism for my specific requirement. That was not possible. So with the advent of this programmable switches, V4 and programmable switches, this actually paved way for providing fine-grained visibility into the networks. So INT gives fine-grained visibility. So how it works is, for example, we have this top of rack switch. We have server racks. We have the top of rack switch, and it goes via multiple switches, because in data center we always have lot of redundant path. This is another top of rack switch. So if it is going, if this top of rack switch, say if it is going here and here, of course we have path here. This INT help us identify which path did my packet take. And it also help us know which rules did my packet follow. And three, how long it also help us identify how long did my packet queue at each switch. Then so there are multiple such queries we can have, or multiple such hard to find informations we can achieve with P4 plus INT. So how it happens is, there are in INT there are each switch will have something called as first, if I have to tell that, okay, if these are the things that I'm going to look for, which rules did my packet follow, I should be able to tell the switch key which traffic should the switch first of all monitor. Okay, so that is one thing. Another thing is, when that when such a traffic comes, it should collect the information, and then it should trigger the event that would actually takes care of sending across the information. Okay, so there are majorly three components in INT we can tell. One will be the watch list, which is nothing but the filter or identify the traffic. That is, it typically tells which flow to monitor. Then we have something called triggers. We won't be interested in monitoring every packet of this flow. It won't be like that, right? Normally what happens is, if it could be simply like if the number of packet for this, if the packet count is greater than 100, then monitor. I mean, it's a simple example, something like that. So there must be a trigger mechanism which will start the monitoring. So watch list will tell which flows to monitor. This trigger or intelligent filtering. This filtering mechanism will tell when to start it and when to start the monitoring. And then we have something called the telemetry report. So the monitor data is collected in a certain format and sent to the sent to a central location where it will be kept and it will be analyzed. So these are the three major components in INT. So first we mention which flow we want to monitor. Then we mention the triggering event, like when to start it, what should be the trigger criteria to start the monitoring, and then third one is once you hit the trigger criteria or the triggering event, then you start collecting the information and send it across to a central location. So I just gave an example of packet count greater than 100. It could be like drop count. So dropping a packet in the flow could be a trigger. So whenever a drop happens, that would be whenever a drop happens, that information will be retrieved, and then the telemetry report will be formed and sent. So there are three ways in which the telemetry report can be sent. One is in INT embed mode, INT MD or embed data. In INT embed, what happens is, so we have this, sorry. So we will have a host, then we will have a switch, which we call the source. So this is where the telemetry, INT telemetry will start. And then in between, we can have multiple switches. And at the end, we will have a sync switch, source and sync. So this will be the sync switch. This will be the source switch. So in embed mode, we will mention the watch list in here in the first switch. So when a packet comes, the packet will have a header and it will have a payload. Now based on the watch list, when this packet goes here, the packet gets appended with header, INT instruction, and also the switch A info, SA info, followed by the payload. These are transit switches. So based on the INT instruction, based on the INT instruction, the transit switches will take the necessary action, whether to what to monitor, trigger, those gets taken care. And then again the header, INT instruction. And this is switch A info, switch B info, switch A info, then payload. So in the sync switch, what will happen is the in the sync switch, they will strip off the INT information, and the INT information will be sent to the monitoring server or somewhere monitor. So this is the sync switch. So here the event will be detected. So in embed mode, all the switches will add the information based on the INT instruction, and then in the sync switch the event detection will happen. Check whether the trigger the event or the trigger have occurred. If the trigger have occurred, then accordingly the INT packet will be formed and sent. So this is one way of doing it. The main disadvantage here is that this guy is becoming large. As the number of switches increases, the packet size is increasing. Sorry, excuse me. The other mode of INT is the postcard. In postcard, what happens is we will have host. There is no source and sink. Every switch will act as a INT collector. So watch list will be there. The trigger or event detection will be there, and header and payload is the packet that comes to the switch. Okay. Then based on the event detection mechanism, INT postcard will be sent. Okay, packet header plus info of A, switch A. Now again, in the second switch also the same will happen. This will also have watch list and event detection, and if the event is detected, again a postcard, INT postcard will be sent. Here also only the header and the payload comes, so the packet doesn't get manipulated or modified at all. So that is how in INT, so all of this comes to the monitor. So this is how it happens in the postcard methodology. Here the problem is that every switch will be sending out the postcard information. So there will be a the packet number of packets exchanged in the network will increase. So another and in addition to that, all the switch needs to have this the packet watch list has to be there in all the switch. So on a per packet basis, this needs to be tested on all the switches. So a mixed approach is normally used, wherein we club both the embedded and the postcard approach. So in the in such an approach, the source switch will have the watch list. The source switch will have the watch list, and when it sends out, what it will do is a header, INT instruction, and payload. This will be sent, and there will be a postcard sent here, INT report. Here again, INT report will be sent. This continues. But the packet header doesn't grow. Only the INT instruction is added. Rest of the information about the other switches are not added. Also, in every switch, we need only the event detection mechanism. The watch list is not needed. So, based on the INT instruction, it will identify, and then the event detection will be performed. So, this is the commonly used mechanism. So, it have actually so the main advantage is that it provides INT provides fine-grained visibility. This actually simplifies troubleshooting. So it actually can add in a lot of other intelligent path selection. So by looking at the cues and reported by the INT, one can actually design a custom congestion control mechanism and can also ask for traffic rerouting based on these information, etc. So one of the most commonly used use cases to get the drop report and queue report, which actually help us identify if there is a packet drop or if there is a congestion build-up happening, queue build-up happening. There are many other use cases as well. So, I mean, we can see any question was there from the INT section the previous year. First one was which of the following statements about INT is incorrect? Yeah, so which of the following statements about INT is incorrect? INT is a network monitoring framework for collecting and reporting. Can you type in the answer? Uh, INT is a network monitoring framework for collecting and reporting network status. Before with INT can find how long the packet did queue at the switch. INT is a framework used to encrypt network traffic. INT uses the PISA framework for telemetry data collection and transport. Yeah, so it is the question is statements about INT is incorrect. Okay, INT is a network monitoring framework for collecting and reporting network status. So this is correct. We all know, right? So this is true actually. And P4 with INT can find how long the packet did queue at the switch. So this is also true. Now, INT is a framework used to encrypt network traffic. So this is false. So this is incorrect about INT. And INT uses the PISA framework for telemetry data collection and transport. So we have seen earlier, right? Before is the programming language used for programmable switches that follow the protocol independent switch architecture, which is the PISA architecture. So PISA before is used for programming such architecture. So this is actually true. INT uses the PISA framework for telemetry data collection and transport. So these are on the programmable switches using before. So programmable switches uses the PISA architecture. So these are all true. This is wrong. So the answer will be C. Now let me see if any other question is there. We have only one question from INT. Okay. So now let's move to the next part that was discussed, which is about computing, right? Let's get into the computing part. So though it is serverless computing, I think the lot of computing architecture have been discussed, right? The monolithic architecture. We have something called monolithic architecture. Then microservice architecture. Let's first take a look at what a monolithic architecture is and what a microservice architecture is. So, in a monolithic architecture, what happens is, let's take an example, okay? Um, let's take an example of maybe e-commerce site which have a client browser. We have a client browser. And then from here we have a payment. We have shopping cart. We have the inventory. Okay, an application wherein you will have the inventory listed, which you can put into your shopping cart, and then you can buy it by making the payment. Okay, this is a simple application. So in a monolithic application, this whole application will be developed as a single executable. So when I say single executable, I think all of you would have I mean in C and CPP, if you program normally in our college labs and all, we actually write it in a single file, we compile it, and we get an executable which we run it. So for example, in C, if you write a test.c program, we compile it using test.c. Then by default the object file name will be named as a.out. Then we execute it ./a.out. This is how we execute. So this is the executable. Okay. So in a for a monolithic application, what we mean is the all the functionality of the application is developed as a single entity, and we get a single executable. Okay, that is the how monolithic applications a single structure kind of. Hmm? But there are advantages here when we develop as monolithic applications. The advantages are it is easy to deploy, It is easy to debug because it's everything is together. The Normally a group of developers would have developed it together, so they will know the in and out of the entire application. And it will be faster because everything is running in the same place. So there is no communication. It's in the single executable, right? There's no communication involved between different, like from the payment to the shopping cart or anything. It is like function calls only. So it's faster. And yeah, that is what for performance. But the disadvantage with nowadays as the applications are growing large, the disadvantage is that as the code features grow, as the code base grow, it become very difficult to compile and test every time we make a small change. So this is the advantages. This is the advantages. The disadvantage is that as the code base increases, it is difficult to compile and test everything every time a small change is made. Even if, for example, we have made a change in the payment related function, it is needed that we have to test the whole application. Then as the code base increases, the complexity also will increase and it doesn't scale well. This is one of the major issue actually. And another issue is fault at one component breaks the entire application. That is, there was an issue in the payment function, okay? And because of that, the application had crashed or something. So what happens is if the issue at the payment caused the entire application to crash, irrespective of whether the shopping cart and inventory related code had an issue or not. So in general, if you see such applications, if you see these majorly, if you take an example of an e-commerce application, and more specifically Amazon or Myntra or where we normally do the shopping, we tend to go browse the site, just keep scrolling around looking at various products, and at max we will put them into the cart. Rarely we actually go do the payment and buy it, right? Until otherwise it is very much needed, we normally don't do the payment. So if you see the frequency at which you go to the site, you scroll through and you put it into the cart, and the frequency at which you actually buy a product from the e-commerce site, it's very different, right? The rate at which you buy will be very low, but the rate at which you go to the site, do the window shopping, like e-window shopping, you can tell, and put it into the cart will be very high, right? So in the scenario, even if the payment had an issue, those users or those public who were just doing the window shopping actually should ideally be able to continue doing, because anyway they are not going to do the payment, so they should still be able to access the inventory and access the cart. But because it is built as a single unit, an issue in any of these will break the entire application. That is one major issue. And another issue is scaling up. If we have to scale it up, like again the same example, when we have the Diwali sales, freedom, Independence Day sale, Republic Day sale, the probability of buying increases, right? On a normal scenario, the rate at which we tend to uh, do the window shopping and put it into the cart, and the rate at which we buy, will be different when there is a sale. And right now, many times it happens we put it in the cart and wait for the sale to come. So during the sale period, the number of people actually using the application will shoot up. So we need to actually scale up the number of instances of the application accordingly. And another aspect is when even when we are scaling, for example, in the normal scenario also, if the application has to be as I already told, the number of people who actually browse through and put it into to the cart is very much higher than the number of people who actually go do the payment and buy it. So, but when we have the monolithic application, we have to scale the whole application. But ideally, I should be able to scale the inventory and the shopping cart alone, because in a normal day, the number of people who would be actually using the payment part would be less. But this is not possible. We have to scale the entire application. It's not possible to scale it like shopping this alone I cannot scale. I have to scale the entire application. So these are the major disadvantage one started observing with this monolithic application. So and thus came the migration towards what is called as the microservice based architecture. So the first among the pioneers who actually moved from monolith to microservice was Netflix in 2009. They migrated their streaming applications from monolith to microservice. They did this because they were not able to keep up with the increasing demand for the rapidly growing video streaming services. Yeah, so that is, yeah. So with microservice-based architecture, what will happen is the same application we will split the payment, shopping cart, and inventory as different services. Okay, so how it will be that there will be a client browser. Mhm. We will have a payment, shopping cart, and inventory. And there will be communication between these. So we develop each of these as separate services. And when we do it like this, no, we can actually when we have a monolithic architecture, we need to have the whole code. Mostly we tend to write prefer to have the whole code written in the same language. But with microservice based architecture, you can write this in I mean all these microservices can be developed independently. So the major advantage is the agility, the scaling, testing, and the flexibility. So if I make any change in the shopping cart related service, it is sufficient to do the testing necessary for that particular service alone. I don't need to do the testing for the whole application or the payment and inventory also. So we can scale it partially. Like for a normal days, you can keep the shopping cart instances as 100 and inventory as 100, whereas payment number of payment service instances 20. But as the sale comes, you can increase all of them to 1000, maybe 1500, 1500. So we can scale it irrespective, independently. Yeah, we can scale the microservices independent of each other. But the disadvantage here is like now it becomes complex. There is communication happening between the microservice. Since there is a communication added, it actually increase the user request latency. Performance wise, there will be a slight dip. So that is with respect to microservice based architecture. Then now let's go to serverless architecture. Okay, serverless computing. Serverless computing can be looked upon as an architectural pattern or a computing model or a way of developing applications. So different people provide different kind of definitions for it. Um, so when we say serverless, it does not mean that it is without any server. Okay, it's not like that, because end of the day, when if you have to run anything, I need a compute. So without a compute, we cannot run it. So it's not that it is without servers, but it means that less of servers. So serverless means that less of servers. So in a serverless architecture or way of development, the application developer does not need to know anything about the underlying server. So that's typically what they mean by serverless. The information about the server or the knowledge that one need to have about the underlying infrastructure or runtime and other things is lesser and lesser and lesser. So in the there have been and serverless computing is the latest in the architectural shift. Okay, so in from the early 20s there have been a shift in the computing architecture, and serverless is the latest one among them. So earlier days we had this notion of physical machine servers on which we run the application. So we have the hardware, we have the operating system, we have the runtime, and we have the application. So this is how we run on a server. We will run an application. Then came the concept of virtualization. So with virtualization, what happened is we started sharing the hardware between different applications. So on a particular machine, we can install another machine. Like for on my Windows laptop, I can spin up an Ubuntu machine like that. So the underlying hardware gets shared between the host window and the guest the VM. Okay, so this is virtualization. So we can have the VM will have the operating system, runtime, and the application. Again, this could be VM2, OS, runtime, and another application. So these two applications are running on the same hardware but on different virtual machines. And then came the concept of containers. So again, in containers, how it happens is here hardware and operating system is shared, but the runtime is separate. Runtime, the application. And with serverless computing, even the hardware, the operating system, the runtime is also same. We have different applications. So this is no sharing. This is virtual machines. This is containers. This is lambda. Mm. So, so to get a better idea, how it would look as. Now, after now with respect to the cloud environment, when we are um, what to say, when we are utilizing the infrastructure or the underlying hardware from the cloud, there are in different ways the cloud providers provide the services. Okay, so we can take a look at it. One is in an on-premise manner. So, for example, an enterprise has a data center in its own campus. So, for example, a company like ONGC or a bank, they all have their own data centers like IOCL or all of them have their own data centers. So they will have everything in their DC, so on premise. So they themselves takes care of managing. So the networking, the storage, servers, virtualization, in case if they are doing virtualization, the operating system, the middleware, everything. Runtime, the data, and the everything will be taken care by the respective people. Okay. Now, when we are moving to cloud, uh, it's not on precise, right, on premise. It's sitting somewhere else. I don't have anything in my home or anything. Right, when you are, for example, using the Google Cloud or something to run any of your application, you don't have the server in your home, right? You are having it is somewhere in their data center. We are utilizing it. So the way they provide these services is one is infrastructure as a service, IaaS, infrastructure as a service. Another is PaaS, platform as a service. Another is SaaS, software as a service, and the other one is the serverless. So in infrastructure as a service, what happens is in this box until the virtualization part, they will take care until virtualization. So this the cloud guys will take care. This we have to. If I am going for an infrastructure as a service, then what I will get is they will provide me a VM. They will literally provide me a VM with no operating system installed. I need to take care of installing Ubuntu or whichever OS I want to, like server OS I want to install. And then on top of that, I run whatever I need to run. I have to deploy my application and run it. So I manage. Now, if you are going for platform as a service, until the runtime, they will take care. Data and application only, I need to take care. This the cloud guys will take care. Others manage. This is what I will have to manage. And in software as a service is nothing we have to manage. In software as a service, everything is managed by other. For example, Gmail, Google Doc, Google Meet, whatever we are using, right? These are all cloud services. So this is software as a service. Everything is managed by the In serverless, what happens is until the sorry. Mm, until the runtime part, it will be taken care, but the data and application part, we have to manage. The runtime part, others will manage. So the cloud provider will manage. So this is the different ways the cloud providers provide the service. So SaaS is something we all have utilized. Um, IaaS, PaaS and all, I think companies, enterprises use when somebody is hosting something in their data center. It depends whether the management is whether infrastructure is obtained and further deployment is taken care by the enterprise, then it is infrastructure. Otherwise, it will be platform as a service. So we'll take a look and try to wind up as I'm unable to speak longer. Take a look at the questions. I'll copy paste it in the chat, or maybe yeah. Which of the following statements is bar are correct? Can you go through the question and type in the answers? So we have seen that in platform as a service. Uh, which of the following statements is correct? So in platform as a service model, user manages services such as runtime, middleware, and operating system. No, a user will be managing data and application. Rest of the part is managed by the provider. So this is wrong. A is wrong. In PaaS, the cloud service provider manages service such as runtime, middleware, and operating system. This is true. In infrastructure as a service model, cloud service provider manages services such as runtime, middleware, and operating system. No, in infrastructure as a service, actually, provider just provides a VM. Installing an operating system in the VM and rest of the things has to be taken care by the provider doesn't take care of that. So C is wrong. Uh, mm, in serverless computing model, provider manages the underlying infrastructure, middleware, operating system, and other data service. So the correct answer is B and D actually. Mhm. What is the disadvantage of monolithic architecture? It is easy to deploy and manage. Yes, it is easy to debug. It is less scalable than other architecture. It is more scalable than other architecture. It is less scalable than other architecture is the disadvantage, right? So answer is it's less scalable. It's not scalable. Mhm. Which of the following statement is incorrect about microservices architecture? Individual components should be loosely coupled, allowing for greater flexibility. And okay, it is incorrect. So this is true. In microservice architecture, we keep them loosely coupled. Individual components or services are loosely coupled, allowing for greater flexibility. Option B is individual components should be tightly coupled. So this is the opposite of the previous one. So this is the wrong statement. Failure of one component does not impact overall service. That is true. Lower risk for building and upgrading the component. That is also true. So the answer here is B. Just the following statement about network processors is not primarily true. I don't know why this came in this week's question. A processor specifically designed for networking application, that is true. Special memory controllers for moving packet data, yeah, that is true. Hardware device that encrypt and decrypt network traffic, that is false. Network processor doesn't do that. It's a high speed processing capability. So C is the wrong point here, which is not true with respect to network processor. Next question is, which of the following statement is bar are correct about software architectures? A microservices architecture is more scalable than a monolithic architecture. That is true. Serverless architecture provides complete control over the underlying infrastructure, which is false. It doesn't have any control over the underlying infrastructure. Serverless architecture has limited control over the underlying infrastructure. That is true. AWS Lambda, Google Cloud Foundation, and Microsoft Azure functions are examples of serverless platforms. That is also true. So A, C, and D is the answer. Hmm. Which of the following statement is incorrect about message delivery semantics? Okay, we didn't see about it. Yeah, there's something we already looked at. Okay. Yeah, so in serverless architecture, there is something called mm, message delivery. So, okay, I think I will get into this. So in serverless architecture, one second. There are basically what happens in serverless architecture is typically uh, developers write the functions and the functions are executed only when it is actually invoked or it is actually needed. Whereas in container or microservice based architecture and all, we will have the containers always running. Whether an application request comes to the container or not, it is always running. Whereas in serverless architecture, it is like execute the specific business logic only when it's like functions as a service. So only functions are invoked and then it's done. So as only when it is needed, it is invoked, it is run, and then further it is there is no nothing is running over there. So basically we have certain components in serverless architecture. First one is the API gateway. So this is the communication layer between the front end and the function as a service fast layer. So front end, maps the REST API endpoints with the respective functions that runs the business logic. So when a request comes, there will be front end will receive it, and based on the API endpoints, the corresponding function for the corresponding business logic gets invoked. So the second component is functions. This will be executed as and when a request comes, okay, via the API. The API endpoint will run the respective function based on the request. So correspond so that the respective business logic get executed. Another one is backend as a service. So in case if some data, persistent data has to be stored, then there is also a backend as a service. So when there is a communication like like how is it ensured that the communication between the API gateway and the functions happens in order? So there are three mechanism that is one is this yeah yeah, the message delivery mechanism. So the so there are multiple ways. One is exactly once message delivery. Next one is at least one. Next is at most one. So, in exactly one's message delivery mechanism, it takes care that the message exchange between happens, and even if there is any drop or any anomaly because of which the message doesn't gets delivered, there will be mechanisms in place which ensure that exactly once the message will be delivered. And at most once message delivery mechanism does not take care of any anomalous anomalous things happening. So there will be it will be sent once, and if an issue happens and if it is not delivered, then it's lost. Whereas in at least once multiple times the same, it will be sent, but there is a possibility that in multiple times the message delivery can happen. So the question is, which of the following statement is incorrect about message delivery semantics? Okay, so in at least once message delivery semantics can result in duplicate messages being delivered. So that is true. Exactly one's message delivery semantics ensures the message cannot be lost or duplicate. At most, one's message delivery semantics provides no guarantee that a given message will be delivered. So it's like a best effort mechanism like we have in our IP. The last is like exactly once message delivery semantics is often used in case where some duplicates or lost messages are tolerable. So the wrong incorrect one is D. That is exactly once message delivery semantics is often used in cases where some duplicates or lost messages are tolerable. So in such cases, we will be going either for exactly ones or at most one, not for exactly ones. So that's pretty much what we have for today. We have discussed the questions. Yeah. So. Mhm. So I'm done. So any queries? Otherwise, we can close the session. I'm really sorry for the kids voice and the cough and all in between. My throat is not well. Yeah, thank you all. I'll close the session. Thank you. Bye.